Good morning, everybody. Today we have a brand new Codeforces round. This is round 767. It's a palindromic round. It starts in 7 seconds. I will be sharing my competition in the round. I'll be mostly pretty focused on what's happening here. And then after the round, I'll share solutions to all the problems that I know how to solve. It's going to be pretty focused on me trying to do well here, though, so I might not have too much commentary during the contest. All right, this person knows about the max, and he likes it so much he decided to use it right away. Given an array of n non-negative integers, we want to make a new array B from the following way. Well, A is not empty. Choose an integer k, append the max of the first k numbers to the array. Apply the max of the first k numbers of A to the end of B and erase them from A, shifting the positions of the ring numbers by A. B to be lexicographically maximal. So you do 0, 1, 2, 3. Oh, so it's just like, what's the maximum? What's the minimum thing not in it? Minimum 0, I guess. And then you have add and remove. So we'll use a tree set, and we'll store, the counts of everything. Okay. Oh, I guess we don't even need a tree set, huh? Because we'll either remove it or use it. So just like an array, it's fine. Yeah. Oh, you also want a bunch of zeros in it too. Oh, it's got to be the first k. Interesting. Okay, so you want to know the max of what's left. That's important. And then you know the max of what's left, and then you need to pot from the front until you get that. So this you can just do in order n, and it's fine because you'll be removing each of these things. And then how do you check the current max? Yeah, you just okay, it's easy. So we don't need any tree sets or anything, just an array. Okay. These are all less than or equal then? Okay. So this is int array frequency, or I guess CS left is new int array n plus 1. Okay, so int n alive equals 0 or equals n. So we'll get the max. So now we have the max of the array. Okay, so now we need to pop until we reach max. Okay. So we'll have array list integer modified. Okay, so while new max is less than max, we need to keep doing this. Okay, so then int at equals 0. So now in prefix at plus plus equals, I guess, int next val equals a at plus plus. Okay. So this is the next value. So then modified.add next value. CS left at next val minus minus. Then we need in prefix at next val plus plus. And then while in prefix at new max is not equal to 0, new max plus plus. Okay, so then we keep doing it until we get this, and then we'll have array list integer ants. Whoa, battery exhausted. Sorry about that. Okay, is new array list. Oh, we need to do this here. Okay, so for I in modified in prefix at I equals 0. Okay, and then we also need ants.add max. And then for and I in ants, out.print, plus a space, out.print line. I just ruined my template anyway. Oh, we also need NLive minus minus. Pass pretests. Looks good. All right, time to fix this. So this is all part of problem A. A is fine. Delete temp. Rename this to temp. And then make this B. All right. On problem B. Please. Peculiar movie preferences. You're given a list S of n non-empty strings of length at most 3 representing scenes in this person's movie. Okay. N non-empty strings, each are length 3. Okay, a subsequence of S is awesome if it is non-empty and the concatenation of the strings in the subsequence is a palindrome. All right. Yes, I see. Okay. A sequence A is a non-empty subsequence if it can be obtained by deletion of several elements. Oh, subsequence. Okay, not a substring. So we have some strings. We have n of them. Each are at least 3. It's awesome if it is non-empty and the concatenation of the strings in the subsequence in order is a palindrome. Okay, so we're picking some of the strings. So we're gonna pick some of these strings. Yeah, we pick some of the strings and then we want pick some of the strings, we want them to be a palindrome afterwards. Okay, so it could be no. Do you necessarily want like 2 strings? I don't think so. They gotta be in order. That's nice. Yeah, you might want more than like 2 strings. So A, B, B, A. Wait, can you have just one? The list has at most, wait. S of n non-empty. At most 3. Man, gotta be careful with this reading. Okay. Each string has length at most 3. So then the answer is gonna be yes. A lot of the time. There just aren't that many no's. Okay, let me think. Okay, we can't have any strings of length 1. Otherwise the answer is definitely yes. Right? Yeah. So we have no strings of length 1. We also have no XX, and then we have no XZX. Because any of these would like imply the answer is yes. So we kind of have like a bunch of edges, right? We've got like A, B, B, A. If we ever have A, B, then we would need, if we have B, A, then this is like, we're done. If we don't, then we have like A, B, and then we have like C, B, A, and then we're also done. Because this is a palindrome. Yes, this is an easy problem, right? Because this is all the cases. So any ones and we're done. Any palindromes and we're done. Otherwise, if we have the reverse of anything, we're done. Or if we have the reverse of anything and one of them is 3 long, we're done. What if we don't have any reverse for a 3-letter? Then it's impossible. Yeah, like because otherwise it's not going to be a palindrome. Yeah. Okay, cool. Let me, thirsty. All right. Got some tea and water. And back to the contest. Okay, so problem B should be easy. And then some end strings. Gotcha, care. All right, so base cases, say boolean is pal. I guess we can just say s0 equals s at s dot length minus 1. Okay. So for char array s in strings, if is pel s, then sys out yes and return. Or continue outer. Okay. Next we have the only other case that matters. That was easy. So next we have two characters to two characters. Can we do an n squared here? No, we can't. It's annoying. Okay. So for each character, ants times equals 100, ants plus equals c minus a plus 1. So now we need a hash map of these things. So we need hash map or hash set of long revs. Now we need for char array s in strings revs.add hash rev of s. Okay, then for char array s in strings. If s dot length equals 2, then we do one thing, otherwise we do something else. If the length is 2, and we also need like 2, 3. Okay. Hash full will be hash of s, right? Yeah. Okay, so if revs dot contains hash full, then the answer is yes. Otherwise, for into add equals 1, to add is less than or equal to 26, to add plus plus. If revs dot contains hash full times 100 plus to add, then this works. Okay. Otherwise, out dot print line. No. All right. So this is terrific. Now we have the size 3 stuff. So for size 3, if it contains this, yes. Otherwise, long hash 2 equals hash new array. This will be size 2, so this will be s at 0 and then s at 1. Okay, should be good. Yes. Ooh, second one is no. No. Yes, yes, no. What is the second case then? Oh. You need to concatenate them in order. This needs to be the stuff after you. Right? This is only the stuff after you. So then, yeah. Looks good. Man, that took me a long time, 20 minutes. Okay, not terrible, not terrible. Ooh, the tricky part of the contest. That was when things get fun. That was also the part of the contest where I regret whatever decision I make if I don't end up doing well. Okay, let's read both. Let's read D first. The difference is the constraints on N, M, and T. You can make hacks only if all versions are solved. Alice and Bob are given numbers N, M, and K. Play the following game. The game has a score that Alice tries to maximize. Bob tries to minimize. The score is initially 0. The game consists of N turns. Each turn, Alice picks a real number from 0 to K. Bob either adds or subtracts from the score of the game. But throughout the game, Bob has to choose to add at least M times out of the N turns. Ooh, okay. Bob gets to know which number Alice picks before deciding whether to add or subtract. And Alice gets to know whether Bob added or subtracted the number from the previous turn before picking the number for the current turn, except in the first turn. What will the final score of the game be? This is a really cool problem. Oh, and it's a fraction too. Okay. Interesting. What are the bounds? N, M, up to 2000. And then here it's big, I assume, right? Oh, only 10 to the 6th. What is K? K is the max. Okay, yeah, that's fine. All right, so that's that. Grid XOR. The XOR sum of a set was the XOR of all the elements. After almost winning IOI, Victor bought himself an n by n grid consisting of integers in cells. N is an even integer. Okay, we have an even by even grid. The integers in the cell and the ith row and jth column is aij. Sadly, this person stole the grid from Victor and told him he would return it on one condition. Victor has to tell this person the XOR sum of all of the integers in the whole grid. Victor doesn't remember all of the elements, but he remembers some information. For each cell, Victor remembers the XOR of its neighboring cells. Two cells are considered neighbors if they share an edge. In other words, for some integers, blah, 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 the cell in the ith row and jth column is a neighbor of the jth row and lth column. One, 5, 1, 5. Yeah, I can do this. This seems easy. I don't know how to do the other one, but this seems way easier than E1 anyway. All right. So here's the idea. We look at the edges. It being even is going to be important. So we've got this here, with this edge and this edge. All right. Oh, it's n by n. N by n. Okay, so we get this one. That gives us these two edges. We want, okay, what edges do we want? This one and this one. You want every node to be part of at least, or exactly one edge. So this one, this one, this one, this one, this one. Now we kind of have problems. I guess we need like this and this. Yeah, so, oh wait, every node needs to be part of one, so this doesn't work. Right, because this top left thing isn't in it. So we want to pick, yeah, we're going to pick like, hang on. So if we pick an odd number of neighbors, of every cell, that would do it. Is it that's the 4 adjacent things, right? Yeah. An odd number of neighbors of every cell. Wait, how do you do it for this one? Oh, just the top two? Yeah, the top two. So what is this? This satisfies everything. Okay, this one's not satisfied. So we can do the one below it. So this is good, this is good. That's good, that's good, that's good. That's good, that's good, that's good. That's good, that's good. These two are in trouble. So this one's fine. This one's not, so we gotta color in this. So now this one's okay. Do I want to make it symmetric? Probably. Oh wait, this is bipartite. Yeah, it's bipartite. So we only have to worry about half the grid here. Okay, so we satisfy this. So we have 1 or 3. Let's try. Well, we can satisfy both of these, right? Oh yeah, we can do this. Wait, this one. Yeah, we can do this. That gets this 1, 1. Then we can do this. And then we can do this. How big can this get? Oh, okay, but this fixes any multiple of 4. Right? Yes. Yes. This is any multiple of 4. No, it's not. Darn. Because you're screwed over here and here. Okay. So let's do this again. So for 2 by 2, we've got this one. Yep. And that handles these two. For 4, we've got, we need to satisfy these. So we do this one, this one, that works. Okay. What about for 6? This is 7 wide. 1, 2, 3, 4, 5, 6, 7. Okay. Okay. And this is just a puzzle, right? So we could do this. Let's try it. Just try the greedy, see what happens. Oh, we're kind of screwed over here. Okay. So this is kind of the greedy. Place it if you can. It's so easy to test too. Well, it'll work for 1, 2, and 4. I guess I might as well just do it, right? Should I do it for 8? Let's just see. So we do this one. Okay, that's solved, that's solved. Then we'll do this one. That's solved, that's solved, that's solved. Then we do this one. We get this. Then we do this one. Wait, how do we get this? Oh. Yeah, this will definitely work. For each row equals 0, row is less than n, row plus. Oh wait, does it work? It might not work. Oh no, it doesn't work. Doesn't work. Okay. Wait, does this work even? Yeah, it does. Okay, so this needs to be taken. Then we get these. Okay, we get these. So oh, I wasn't even doing the greedy, was I? Yeah, you can take this. I screwed it up. Yeah, but this works. This is a totally different thing. Yeah, okay, now it works. If it works for the first four, it's got to be everything, right? That's how primes work, right? 3 is prime, 5 is prime, 7 is prime. Clearly, all the odd numbers are prime. Okay. 4 and I equals 0. Than the n plus 8I equals FS dot read array size n. Okay, Boolean array counted. This new Boolean array n by n. The n for n equals 0 less than n plus and j equals 0. Less than n. If not counted at ij, then throw null. All right, so good there. Then we just need to do this the right way. Okay, so for int x equals 0, or int I equals 0, less than n I plus plus, int j equals 0, j is less than n, j plus plus. If I plus j mod 2 equals 0, not equal to 0, then continue. And we'll do the same thing, but with I starting at n minus 1. And if it's equal to 0, wait. Yeah, if it's equal to 0. We'll continue. So, int array dx equals -1, 1, 0, 0, and we want dy. Okay. All right, so we need int legal, or int okay, so if counted at xy, then continue outer. Otherwise, we do this whole thing again. And then we say ants equals 0, ants XOR equals AXY, IJ. Okay. Oh. We're good. Come on. Come on, Codeforces. Come on, Codeforces, you can do it. Oh, I'm too late. Wait, maybe I did it. No, I'm too late. Oh, 1 second away from okay. All right, not terrible, not terrible. Let's do problem D. Most satisfying part of the day, other than oh, that is awesome. That is so, dude. Okay, I have to. Wait, hang on. I have a lamp, right? It's like an Amazon lamp. It's got the light and then the thing around it. I threw it like this. It landed in the lamp. Oh, this is so cool. I kind of want to just get the camera. If this wasn't the middle of a contest right now, I would get the camera and it is legend. You'll just have to take my word for it. That was awesome. I'm such a ninja. Okay. All right, back to this. So we've got. Oh, okay. Yeah. All right. Let's think for a minute. Bob either adds or subtracts the current score from the game. But Bob has to choose M of the last N. So I guess there's just an easy DP, right? We've got, we can do like DP at N turns. And then N Bob has to pick. Equals the score. I guess maybe let's do some observations here. So Alice can always get K times Oh wait, Alice can't always get that. What is k? Is k just a multiplier of the answer? I suppose so. Yeah, k doesn't matter, right? Alice just scales everything up by k. Yeah, so let's just multiply by k at the end. Okay, so yeah, so let's just play this game as like a DP now. So we've got some sort of DP. Oh, we've got a DP where there's some number of turns and Bob has some picks left. So oh, is this that weird fraction thing? There's this Stern-Brokat trees. I wonder if this is Stern-Brokat. Could be. Could definitely be Stern-Brokat. There's a certain value in, that might be D2 Stern-Brokat. So, okay, what does this DP look like? So if n turns equals the number of Bob picks, then the answer equals, well, okay, so it's always going to be at least 0. Yeah, it's always going to be positive. So if the number of turns equals the number of Bob picks, then the answer is the number of turns. Okay. What else? If n turns equals 0, or if n Bob picks equals 0, so we'll definitely get D1. We might not get D2, but we'll see. If the number of Bob picks equals 0, then the answer equals 0, because Alice will want to choose 0 every time. Otherwise, Bob can choose to pick or not pick. So yeah, so what is keep? I guess like use or not use. Let's just read this. This is why we use pencil, ladies and gentlemen. Otherwise, Bob can use here or not use. So if we use, presumably there's going to be some equilibrium. Which is a fraction. What do we get if we use? we have n turns, we have dp at n turns minus 1, and then pix minus 1. Minus now. Otherwise, we have dp at n turns minus 1, and then we have pix plus now. Okay, so what does this graph look like? We pick whichever one of these is smaller on the x, so this is like the res, and this is now. So when now is really tiny, the pick is going to be important, so we'll want to keep it. Yeah, when n is really small, oh, we'll choose to use it. When now is really small. No, when now is really small, we'll give to Alice. So it increasing would increase with the score. So we'll get this, and then we'll get this, yeah. So Alice wants to pick when these are equal. Yeah, makes sense. Okay. So yeah, so now is now equals the sum of these over 2. Average of results. Oh wait, so no, now doesn't equal this. Our current value equals this. Yeah, this is always going to be smaller, right? Or this is going to be bigger? We have 1 fewer picks, Alice will do better? Yeah. This is a bigger number. Oh, so like answer equals average of 2 future answers. The average? Really? I guess so. Okay, so now I see how this is going to be very quick. This is Pascal's triangle. This plus this over 2. This one equals this plus this over 2. the only difference. NM and T. What is T? 1,000. What is D2? T. 10 to the 5th. 10 to the 5th. Ooh, that's annoying. Wait. Oh, because K doesn't matter. Let's just get our D1 points for now. This is n turns. Int n picks equals this. Int k. Do I have? I got this. Yeah, it looks good. All right. Static int go. Okay. T is new int array. Okay. Add a b, multiply a b. This by half. And we should be good. So int equals multiply, go and turns and picks by k. Darn it. I filled the DP with 0. CLE? What? What? I am a idiot. Negative IQ over here. Oh, how many points did I just lose? Some points. I've got it, right? I've got it. Yeah, good. Okay. Dang it. What? No. Yes, I can submit. All right, oops, okay, so then, yeah, what are we, okay, that was very unhelpful, this wrong submit here. Let's get D2, because D2 is easy. Man, it's rough at the top, isn't it? Ooh, struggles. This is a perfectly difficult round though. Ben Q and -1 and B. Yikes. Wait, what was B? I thought B was a cool problem. Maybe to take a bit. Okay, yeah, D2 is our problem here. We got 38 minutes for D2. So it's similar to Pascal's triangle, right? Did I just code the entire thing with you looking at my face? Sorry. Sorry. I'll try and fix it next time. Oops. Anyway. Okay, D2. Oops. There we go. I got it. Yeah. Anyway. So yeah, oops, my bad. It's hard. Okay, I'm spending a lot of mental energy. I apologize. I'm spending lots of mental energy trying to solve these problems and get my red back. Okay, so we've got some stuff is happening. So this is this, and then we've got these two. So this is one turn. I guess this is 0 turns. 0 turns. 0 picks. And what is the value here? Value is 0. Okay, this is one turn. So this is 0. This is 1. This is 0, and this is 2. All right, so let's say we're here. We need the number of ways to reach this, 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 and this. Yeah. That is annoying. We got to do it fast per test case. So we have, if we're getting this 3, yeah, so I guess we can go to the 4. Just have this be 0. So we need the sum. Okay, so we need, well, let's just write it out. So it's 4 times we have 0 to pick. We need to pick -1 of them. 0 choose -1. Okay, plus 3 times oh, but we multiply by 1/2. Yeah, okay. Plus 3 times we have 1 choose 1. Divided by 2 to the 1. Plus 2 times, so 1, 2, 3. 3 choose 1. Over 2 squared plus 1 times 1, 2, 3, 4, 5. So 5 choose 2. Over 2 cubed. Should we make sure this is actually the formula? I guess really this is the only part we care about. By multiply. By half. Okay, so then this is 2, 1 times 3 times, or this is 5 times 2 times half times half times half. Okay. And then this is 1, 2, 3, 4 turns. 1, 2, 3. So 1, 4, 3, and 1. Nope. It's like half as much. Why is that? It's the average of these two. Oh, because you can't go right down. Yeah, this isn't 3 choose 1. Wait a minute. Whoa. This is cool. We make each of these 1 and then you can get multiples. Okay, this is 2 choose 1 and this is 3 choose. Wait. Okay. 1 choose 1. Yes. So 2. So you're right. 2. You need to go up once. Yeah. 3 choose 2. Right, 1, 2, 3, up 3 times. Wait, 1, 2, 3, up twice, yeah. Yes. Is it half by half? I guess let's just see if it works. What if I just print out a 2D grid times 2 to the n? Guess it doesn't hurt to try. Okay. Wait a minute, what? Okay, so this is 8. Why is this 8? So this is just the sum of the two above it. Everything is just the sum of the two above it. Yeah. Okay. N times 2 to the n. Makes sense. Okay, so we just need Pascal's triangle, but with it slightly modified. Ugh. Yeah, so what I'm doing is all right, yeah. So that's 1 times 2, 2 times 2 squared, 3 times 2 cubed, 2 to the 4. Okay. This is not a terribly hard problem to solve. It is, in fact, something that's very difficult to solve in 19 minutes. And I'm sorry. We'll just leave it at this. How about that? Okay. Ah, my bad. So, yeah, I did this pattern, printed out the whole grid, found the pattern. Here's what we got. And this is, according to OEIS, and times 2 to the n. That's where I'm at. Okay. All right. So now we have to do this in 20 minutes. 19 minutes. We need a version of Pascal's triangle that's like modified. Yeah, this is tough. So this is 0, 0, 0, 0, 0. Well, it's not 1, 2, 3, 4. It's like 2, 8, 24, 64. What if we just look up this? This would be cool. There's a 2D OEIS thing. Okay. 64, 160. So then this is 2, 2, 2, 10, 12, 34. What's 12 plus 34? 46, and then 98. All right, so we've got this. How do you figure out a thing? So 12, or maybe 46. We hit 24 once. We hit 8. How many times do we hit 8? Same number of times we hit 10. $50. What if we look up like 214.46? Man, how do we calculate this? This can't be that bad. Man, I really want to know. We hit this once. How many times do we hit this? Does it matter what this thing is? So this is 2. It's 8. We multiply 8, or we 8 plus 8. Okay, this 8 is just 2 times 2 squared. And now we want it to be 3 times 2 cubed. So what happens here? Divide by 2 times 3. It's kind of messy. Yeah, how many times do we hit 8? The same number of times we hit 10. Okay, so we hit this times 2. We hit this 1, 2, 3 times 3, and this times 4. Oh, so it's cumulative sum stuff. No, it's not. So it's like 4 choose. Man, how do you do this? Oh, mathemagic. This is like 1, 2, 3. Yeah, 1, 2, 3. 4 moves. So 4 choose 1. Times 0 plus 1, 2, 3 choose 1 times 2. I guess we do have a 2 to the n here, kind of. Maybe it's different. So this is what, 16, 6, 0. This is, yes, that's right. Okay. How do we evaluate this quickly? This is the same as 4. Well, we don't need to worry about that. Yeah, we do. 4 choose 1 times 0 times 2 to the 0 plus 3 choose 1 times 1 times 2 to the 1 plus 2 choose 1 times 2 times 2 to the 2 plus 1 choose 1 times 3 times 2 to the 3. It'd be nice if we could like combine these terms somehow. Maybe we can. Maybe this is just a thing. Because this is like n is decreasing, but this, the 2 to the power is decreasing. So maybe these like wind up being something similar. And then we're left with like 0, 1, 2, 3, and it all works out. I don't know. So looks like unless we fail system tests, I'll get IM back, get a decent rating boost, but not getting red back here. Yeah, so I need like plus 23, which will happen. Plus 72, yeah. So I'll get like part of the way there, part of the way back to red. Oops. Okay. How are my friends doing? Man, everyone sees D2. These geniuses over here. How do they see it? Man, even these fools. How? How? Maybe there's just an easier way of doing it. I really want to read these people's code now. And it looks like E is also on the table, but for a lot more points. Oof. I have to pay respects there. It's gonna hurt. All right, what is this? It's like sum of I times 2 to the I times like n minus I plus 1, choose k. I don't know the formula. I haven't seen this before. How do you? Yeah, I should know how to do this. Okay. Sum. Well, I can't Google this. Oh wait, that's actually cool. No, it's not. Okay, it's not helpful. I don't even know what I'm looking for here. Yeah, I don't see the math. Should I have read E? N buildings 1 to N, some buildings have roads between them. There's exactly one simple path from any building to any other building. Every road has a meteor danger level. The buildings are all grocery stores, but you only care about the open stores, of course. Initially, all grocery stores are closed. Oh, so these ones open. Okay. This range close. Find the maximum danger level on a simple path from X to any open grocery store. Wait, what? Oh, we've graph. We've tree. Okay, we have a tree. What has danger levels? Oh, with roads. Okay. This isn't that hard of a problem, I don't think. maybe link cut trees or something. Yeah, we have a tree, and we just need to know what's the maximum edge with something on the other side of it. Yeah, so just cut the tree, maximum the component, right? Or cut the, I guess it's tricky. To an open grocery store, which change. Yeah, cut the edge, we need to know how many open are on the other side. Yeah, so, but you can do a parallel binary search, I think. Parallel binary search with link cut trees. Seems pretty plausible. Yeah, I think that works. If you know, like, yeah, you want to say, is it bigger or smaller than this many components? Oh, maybe it's tough because you have like a bunch of operations you have to do. It might be very difficult. Whoa, this is a weird scoreboard. Didn't go for B or C. Got D1 and D2 and E. I guess. Yeah, I don't know. It's like people have had a very successful, oh man, am I even gonna be top 200? Unlikely, possible. I guess we'll see. Yeah, a whole bunch of submits are probably coming at the last minute here. I don't know, top 200 Div1's not terrible. Especially when we got about 1,000 people competing. Oh, 200, maybe 201 or something. But possibly a couple people will fail system tests. Yeah. So, I don't know, about a +50 rating boost for me. Not terrible. I'll take it. Things went pretty clean. This is a dumb submit. That's fine. Don't know how to do D2, and I really should. Yeah, tricky, I guess. So now we talk about solutions to all of the problems. We can do that. Yeah, A through D1 were easy. These three I don't know how to do. Yes, yeah, let's jump into solutions. What do you say? Okay, so here we go. Solution time. Problem A, maximum array. So I guess let's read the Div2 problems maybe. Div2 A and B might be easier. People might be interested in them. Okay, yeah, so it looks like we'll just talk about the A and the B then. A, download more RAM. Did you know that you can download more RAM? That's pretty cool. There are N shops. I think that this is a reference to like a meme. There's a website where you can download more RAM. It does that and it like speeds up your computer or something. It doesn't actually do anything, but, or no, downloads a picture of a RAM. There are N shops, or there's a shop with N different pieces of software that increases your RAM. The ith RAM takes AI gigabytes of memory to run. You get the RAM back after it runs, and gives you an additional BI gigabytes of RAM permanently. Each software can only be used once. Your PC currently has K gigabytes of RAM. Note that you can't use a RAM increasing software if it takes more gigabytes than what you have. So you want to print the most you can achieve, so it's pretty straightforward. Basically, you will try and use them from smallest to biggest in size. So that's the idea. You sort each of these objects by their AI, and then you use it if you can, don't use it if you can't, and you just find the sum of the b's that you used plus your initial value. Yeah, so that's Div2 A. Pretty easy. GCD arrays, consider an array of all integers in the range L to R. If L equals 3, R equals 7, you have this array. Okay, so you have like some array of continuous numbers. Given L, R, and K, is it possible for the GCD of A to be greater than 1 after doing the following operation at most K times? Choose two numbers, permanently remove one occurrence of each from the array, insert their product back. Okay, so key thing, GCD of any two adjacent numbers is going to be 1, right? Because they share no factors. So that means for every pair, like that means every time you have, every time you've got two adjacent numbers that haven't both been removed, that means you're gonna have problems here, right? So let's do an example. Let's say you have 3, 4, 5, 6, and 7. In this case, what you can do is you could combine 3 and 4. And if you don't combine 5 and 6, they're going to have a GCD of 1. So you need to combine 5 and 6. And then you're left with this 7 here. So yeah, you have to combine the 7 with something. This isn't going to work on its own because this is going to be like 7 won't have a multiple of 3. Like these two elements won't share a multiple of 3. So yeah, so either the answer is going to be like, if you can, okay. So if you start on an even, then you need to combine everything so that it's even, right? Then you make everything even. Otherwise, I guess that's what you always do. I guess you always try and make everything even. Yeah, you always try and make everything even. So you can count how many even numbers are in the range, and then the number of odd numbers in the range is the number of moves you need. And I think that's just the case. Correct me if I'm wrong, but that seems to be the case. Yes, the answer is no for 3, 4, 5. Okay, yeah. Yeah, so the number of odd numbers in the range is how many moves you need. Unless there's only one number in the range, in which case it's true. You don't need any if that's the case. Okay, that's B. On to Div2 C, which is Div1 A, max in the array. So in this problem, you have some array of n integers, and a bunch of times what you're going to do is take a prefix of this array, delete this prefix from your array, and then add the max of that prefix to a new array. And you want this new array to be lexicographically maximal. So you want the first element to be as big as possible. And then if possible, you want there to be a second element and you want it to be as big as possible. And then of all of the ways of doing that, you would like if there's a third element, if possible. But first, those two things are more important. If you can do both of those, then you want a third element as well. You want this third element to be as big as possible. So yeah, that's what lexicographically maximal means. And they probably explained what it means somewhere. I don't know, maybe not. Lexicographically maximal. So what's the idea? Well, the key observation is that as you include more numbers, your max is never going to get smaller, right? It might get bigger, but the max of a set will only increase as you increase the numbers in the set. The reason for that is just the definition of max is the smallest number not in a set. So as you add more numbers, you might hit the max. As soon as you hit the max will increase by 1 or more if there are things bigger than it in the set. So if you hit the max will increase. But if you don't hit the max, as you add stuff, the max will at worst stay the same. So you know what your first number can be. The first number in this array you make can be the max of the entire array. And once it is that, you want to stop the things you delete as soon as possible so that you get that target max. So you're going to delete the maximal or the minimal prefix to get that biggest max possible. You do that, and then you just keep going, and eventually you'll have done it enough that you just get like the max every time until you're done. Okay, how do you actually do this in a fast way? So first of all, you can get the max of the array in order like number of things left in the array time. You can just iterate through all of the values from 0 up until whatever the max is, and then stop once you hit something that doesn't occur. And the reason is, every time you find this max, if the max is 7, that means when you delete elements from the front, you're going to have to delete at least 7 elements. You're going to have to delete a 0, 1, 2, 3, 4, all the way up to 6. So you'll be deleting 7 elements. So even if it takes you order 7 time to find that 7 is the max, that's going to be okay, because you're deleting a bunch of elements. Then you need to figure out, okay, how many elements do you have to delete for the max to be 7? Now, answering that question really fast is tricky, but you don't actually have to answer it really fast, because if you delete some of these elements, you don't have to worry about them in the future. So you can just keep iterating through the beginning and being like, okay, if I delete this, does the max increase? If I delete this, does it increase? And your runtime can be the order of the number of things you delete. And then in the end, your runtime is just going to be order n. It's probably easier if I show the code for this instead of just like talking about it. So here's what the code looks like. We can do this. So this is the array, and this is some like counting sort. It's like the frequency of how many times each thing appears. Yeah, so initially I just store the frequency of every element, and then I store how many things we have alive, and also this is like how many things are in the prefix which I've deleted, because I need this prefix to have the same max as the max of the array. And this is the element that I'm at. Okay, so I'll talk about what I use this for in just a minute, but now I'm going to go through, and until I've deleted everything, I will find the max of the things that are left, and then delete the prefix that I need in order to have that max. So that's what this loop is doing. So first I find the max of the things that are left. Basically, I just iterate through the frequency of everything that's still in the array, and I keep increasing my max until it's something that doesn't appear. This is safe to do, like this isn't going to kill my runtime, because I know whatever my max gets to, I'll delete at least that many things. So this is runtime safe. I also know that it will appear by the pigeonhole principle, because my array has n+1 holes and only n pigeons. So there's going to be one empty hole. Pigeonhole principle at work. Okay, so then, yeah, this is just the answer. I'll talk about what this does in just a minute. But basically, now I'm going to store this prefix sum I'm going to store in my prefix what is the frequency of every element, so that I can get the max of the prefix. Okay, so the key observation here is as I add more things to this prefix, the max might increase. So I'm going to be doing basically this while loop here, but I'm going to be doing it with this prefix array instead. So yeah, I'll have this max which I'm keeping track of, and every time that I get some new value, I will increment the number of times it appears, And then as long as my new max points to something that I've seen in this prefix, which I'm about to remove, I'll make my new max bigger. I also need to maintain a couple things. So I need to maintain the frequency in this main array, because this while loop will happen again. And I need to maintain how many of these elements are still alive, because that's important here. So I need to get rid of both of these. Also, this in prefix array, I need to reuse it without remaking the entire array, because this while loop might run a whole bunch of times. For instance, if the array is just like all zeros or all zeros and ones, this loop might run a bunch of times. So I can't remake this array the entire time, because otherwise my code would be n-squared. So I only want to clear out the elements in this array that I actually change to be non-zero. So I just make a list of which ones I change, and then I'll zero them out afterwards. That's what happens here. All right, that's problem A. That's the idea. Then I print out the answer at the end. That's how you do problem A. Hopefully that makes sense, or problem C in Div2. Okay, let's move on to problem B in Div1, or problem D in Div2. Peculiar movie preferences. So in this problem, you're given a bunch of strings of length at most 3. And you want to see, is there at least one subsequence of strings? So can you pick some of these strings so that if you concatenate them in order, you get a palindrome? Let's do an example. In this first case, we're given these 2-letter strings. So we're given ZX, AB, CC, sorry, this was, ZX again, and then BA. In this case, if you pick this AB, the CC, and the BA, you get a palindrome. You would get, get a fresh sheet of paper here. You would get AB, CC, BA. So the first obvious thing to notice is this CC is unnecessary, right? We can just as easily get AB and then BA. Another thing to notice is also the AB and the BA are unnecessary. We can just get this CC. So clearly, if any of the strings in this set are palindrome, that means that we're done, right? So obviously, maybe this should be pretty self-explanatory. Any string of length 1 is a palindrome. So if we have any like 1-character strings, that means we can just exit immediately, right? If we have anything that's 1 character. Also, if we have anything that's 2 characters, right? If we have like an XX, then we're done. So we can handle that easily. Also, if we have like X and then we have something else and then we have another X, then we're also done. We know this is a palindrome. So that only leaves us with a couple cases. We can have like an XY, or we can have like some ABC, where A and C are different. Okay, those are the only 2 cases. So now let's talk about what this palindrome is going to end up looking like when we're done. We're going to need to start with something, right? Let's say we start with like a 3-letter thing. So we start with like ABC. This is the beginning of the palindrome. What does the end of the palindrome look like? One possibility is it ends with BA. If that's the case, if we have a 2-letter BA at the ending, we can just keep this first one and the last one, and that's it. If it ends in a 2-letter word, it has to be BA. It can't end in any other 2-letter word, because otherwise that wouldn't be a palindrome. So if it ends in a 2-letter word, we're done. And this is if it starts with a 3-letter word. What if it ends in a 3-letter word? Well, it has to end in CBA. So if it starts with ABC, it's got to either end in BA, in which case we're done, or it has to end in CBA, in which case we're done. It can't end in a 1-letter character, because we've already, if there's any 1s, then we're done, right? We've already eliminated the case where there's a 1. So if it starts with a 3-letter word, then it's very easy. The only other case that's left is what if it starts with like an AB instead? Well, it starts with AB. It has to end with BA. Now, there are 2 possibilities here. Either there's some 3rd character, right? There's a CAB, but in this case, we're done because this is a palindrome. ABCBA is a palindrome. The other possibility is it ends in just BA. We have AB and then BA. And in this case, also we can stop right away because AB and BA just match. So that's the idea. If this is possible, it's possible to do using either 1 or 2 strings, which makes it very easy to check because there just aren't that many possibilities. I guess we can talk about the implementation here. So yeah, we get all the strings. This is palindrome method doesn't actually check if it's a palindrome. It just checks if the first and last characters are the same, which coincidentally is true when your string lengths are 1, 2, and 3. So if any of the strings are palindromes, then we're good. That's it. We're done. Otherwise, I'm going to go through the strings backwards, and you'll see why in just a minute. But basically, I want to add the reverse of each string to a hash set. I store these as longs, but really you could probably just store them as strings and that would work fine because they're all small. Then I case out whether the string has length 2 or 3. If it has length 2, we have this one case, which is AB followed by a BA later. So we want to see, is there a BA that we've seen already? If there is, we're done. Otherwise, we want to see, can we add any character from A to Z to make this be successful? And that's what we check here. And if so, we're done. Otherwise, we're not. So yeah, this is the 2-character case. For the 3-character case, either you need the reverse of the 3-character, or you need the reverse of the first 2 characters in the 3-character. And that's what this checks. And those are the only ways of doing it, as we've proven earlier. All right, that's problem B. Let's talk about problem C on a non-crazy zoomed in screen. Yeah, okay, so we have the XOR of some grid. Okay, so we're given, there's some 2D grid, which we don't necessarily know about yet. We need to determine the XOR of all of the elements in the entire grid. What we're given is, for each element, we're given the XOR of its 2 or 4 neighbors. We have the additional constraint that the size of the grid is even. So, how do we solve the problem? Let's look at this for a minute with some paper. Okay. So, first thing to notice is the following. When we have an element on the grid here, when you've got some element, the number we're given at this position is the XOR of the things around it, right? So if we have some grid that looks like this, you can imagine, I guess I'll just make a 4x4 grid here. You can imagine checkerboard coloring this grid here, right? So it's just a checkerboard pattern. And this is a common idea with grid problems, which is when you're only interested in the things that border you, you wind up with a grid that has like a bipartite coloring. We're going to color the grid like a checkerboard. So when we do that, if you look at some position, all of the information you're given for some grid space is about things that are of the same color, which makes this like easier to think about. What we want to do is we can figure out which white squares we pick, and the white squares we pick will correspond to satisfying all of the black squares. So we don't need to worry about other white squares when we're choosing which white squares we pick. We only need to worry about the requirements given to us on the black squares. Okay. Last thing is, this is just kind of like you think about it and you decide to do it. To me, it was very clear. The answer is going to be the XOR of some subset of the input. And that's just kind of like a thing you predict. So I'm like, yeah, this is probably going to be what it's like. That's kind of just a gut feeling. I don't really know how to explain how I got there, but yeah. I mean, like, it seems to make sense because the numbers you're given, they could change them, and they could just give you a bunch of random numbers, right? And the only information you have is like the XOR between them. So that's really the only thing that's going to end up showing up. I don't know how to prove that or convince you should see that, but that's just kind of how it works. So what we're going to do is we're going to try and find some elements in the input where if we pick them, if we XOR them, then this will give us every element in the output exactly once. So for some square, if we need to pick this square, that means of its 2 or 4 neighbors, we need to pick an odd number of them, right? So if we pick just this element here, if this is the only element that we're picking in this group of squares that we pick in our XOR subset, this will be counted. If we pick an even number of them, it won't be. It'll be included and then excluded. So we need to find a way of picking some white squares here so that every black square has an odd number of neighbors. In fact, it kind of is easier if we think about it so that every black square has exactly 1 neighbor. I don't know if it's possible for like a black square to have 1 neighbor and a different black square to have 3 neighbors and no black square to have 2. I suspect that it's not, but I don't actually know. So yeah, we're just gonna try and have every black square have exactly 1 neighbor. And this is not too hard to do actually. So in this example, it turns out we can just use a greedy approach where we just go top left to bottom right in row major order. And we highlight something if we can. So yeah, this is actually slightly backwards. Let me choose the other version because I know it'll work because that's what I did in contest. So we're gonna switch which squares are black, which squares are white here. Okay, so we want to pick some squares so that every black square has exactly 1 filled-in neighbor. So let's pick this square here. So now we've satisfied this square and this square, which means we aren't allowed to pick this, this, or this. Then let's continue in row major order. So we'll continue across. We'll pick the first one we can. We can now pick this one here. So we'll pick it. And now we've satisfied this here, this here, and this here. So we can't pick any of their neighbors. Let's continue in row major order. Oh, we got this one. We can pick it, so we pick it. Okay. So now this satisfies all of the black squares. Every black square has at least one neighbor. Let's do this again for a 6x6. And then I don't have a proof this works, but I tested it and it does. Okay, so you might be wondering, what about the other things? Well, if we mirror it, then that'll handle the squares of the opposite color. So yeah, that's it for that. Let's color in our black squares here to make this a bit easier for us. Give me just a minute here. Okay. So we want to pick some red squares so that every black square has exactly 1 neighbor. We're going to do this in the greedy way. So we're going to go top left to top right. So we can't pick any of these now. Then we'll pick this. So now we can't pick any of these. Again, we'll pick this. So we can't pick any of these elements. Keep going row major order. Then we'll pick this. So we can't pick either of these. Then we'll pick this one here. So now we can't pick this. Keep scanning, we'll pick this. Now we've satisfied everything. Yeah, so there you go. You can double check this. It turns out this works in general, so you just have to implement that, which is pretty easy. Here's what the code looks like for it. Yeah, so this is just the grid, and we're gonna pick some elements, XOR all of those elements, that'll be our answer. I make this Boolean array for whether each thing has been counted. And first, I check can we pick this element? We can pick it if none of its neighbors have been counted. Also, I'm only looking at, in this example, the white squares here. And then I do the black squares mirrored in reverse after. Okay, so I'm only looking at the white squares. And if it's a black square, then I skip it. Okay, so if it's a white square and none of the neighbors have been picked, then I'm gonna pick it. So to pick it, I will include this in my answer. So this will XOR my answer by whatever its value is. And then I have to mark all of its neighbors as being counted once. So we'll do that. And then I do this with the other type of squares. And then finally, this is just for sanity check. I make sure everything got counted exactly once to make sure this pattern actually works, like the greedy method actually works. And then this is just how I tested to make sure that I wasn't gonna get my answer. I just tested it with like all the numbers up to 20. So yeah, because I didn't have a proof, but it felt like it was pretty good. And then I put the answer. Awesome, that's the solution to problem C. Okay, finally, let's talk about problem D1, game on sum. So this problem is quite cool. I liked it. Let's talk about what happens here. Okay, we're gonna use this paper to explain it. Running low on paper, okay. Yeah, here we go. So, what is the problem, first of all? You have a game theory problem, two people playing a game, and Alice wants the score to be as big as possible. Bob wants it to be as small as possible, which is kind of pretty reasonable. That's how like chess works, chess engines work like that. Yeah, that works. So Alice wants to maximize the score, Bob wants to minimize it. And this is a hot game because you want to move. Actually, it's not really. The two players are different, right? So it's not even a fair game. But we know Alice is gonna get a score that's at least positive, because Alice can always get a score that's 0. So Alice will have a score that's positive because she'll only pick a number that's bigger than 0 if she can do better. But what is the game even? I haven't explained. So you get some score. Every turn, Alice will pick a number, and then Bob will pick whether to add or subtract that number from the total of the game. Bob wants to subtract whenever possible, but Bob is only allowed to subtract so many times. So otherwise he'd just subtract every time. In particular, Bob has to add at least m times. So he will subtract n minus m times. Of course, he's going to subtract exactly n times. So yeah, that's what's going to happen because Bob wants to subtract whenever possible. We also have this like kind of, they decided to try and make it a bit tricky by saying there's a number k and Alice picks a number between 0 and k. Obviously, you can just scale this game up by any integer, right? You can multiply everything by k, no one will change their decisions. So the k doesn't matter, you'll just multiply k in at the end. Yeah, k is very irrelevant. So basically, we'll just say Alice picks a real number between 0 and 1, and Bob will pick whether to add or subtract. Each turn, he does it optimally. So the question is, if both players are infinitely smart, what does the score of the final game end up being? So we can make a couple observations right off the bat. Obviously, if Bob has to add the rest of the numbers, so if n equals m, the answer is just going to be, we'll assume k is 1 here, then the answer is just going to be the number of turns that are left. And also, if Bob can subtract every time, then Alice is never going to, like, if Bob has to add every time, Alice will pick the biggest number possible. And similarly, if Alice, or if Bob can subtract every time, then whatever Alice picks will get subtracted from the score, because Bob's always going to subtract. So Alice is going to pick 0 every time. So if n equals m, then the answer is going to be n or m. And if m equals 0, do I have this backwards? I have it backwards. If n equals m, the answer will be n or m. If m equals 0, that means Bob can subtract every time, then the answer will be 0. So now the interesting part is, what if it's not like that? Well, the next observation is it doesn't matter what the score of the game is so far as what the score of the game will be in the future. You might have some points, you might not. Regardless of how many points you have, you're still going to play to maximize your points in the future. Those can be like a sunk cost. So we can do a DP, because the only effective state of the game is how many turns there are left and how many chances Bob has, or how many times Bob has to add. In other words, how many times Bob is allowed to subtract. Yeah, so let's talk about what this DP might look like. All right, so we're gonna have some DP. It's gonna be DP of the number of turns left, and then also the number of adds that are required. So we have these base cases. So we have if n adds equals 0, then the answer will be 0. And then we have if n adds equals the number of turns, then the answer will be the number of turns, assuming k is equal to 1. So these are the two base cases. Otherwise, what's going to happen is Alice is going to pick some number. Bob will pick whichever of the two options is better. So the two choices are the following. We have let's say the value Alice picks is p. So we have either dp of n turns minus 1, and so this means that here Alice, or well, the turn's gonna happen. So here Bob can either add or subtract. So let's say Bob will chooses to add it. This is n adds minus 1. And in this case we add p. The other option is we have dp of n turns minus 1. And then Bob can choose to subtract. So this is n adds minus p. Here are the two choices. So in either of these choices, Alice gets to choose p, but Bob gets to choose whichever one happens. But really, we know which one Bob's going to pick. Bob's going to pick whichever one gives him the smaller answer. So really, we're going to get the min of these two. Let's look at a graph for the two choices, what ends up happening. So initially, if p is a really small value, if p is like absolutely tiny, let's say p is 0, there's no reason for, like, Bob's clearly going to use up one of his adds to make this happen. So Bob's going to pick this one if p is really small, because that way he gets to use up one of his adds here. So if we're adding p, the result is going to be, it's going to be something like this, right? It's going to be increasing as p increases the result. So this is the p we choose, and this is the answer for the dp. But then at some point, what's going to happen is these two values will become equal. And once we start increasing p, choosing to add p will hurt more than using one of the adds, right? It won't be worth it to continue adding p. So at some point, this is going to start decreasing. And then as p gets bigger, since Bob is subtracting it, the result will get smaller. Eventually, it might even get negative. So the value Alice wants to choose is the value with the biggest possible answer, and that is right here at this apex, which is when these two things are equal. So it turns out that's actually the average of these two dp values. So this dp value is equal to the average of these two, which is really nice. We don't even have to worry about what p is. We can just say it's the sum of these two divided by 2. And that's where the solution comes from. So yeah, for D1 anyway, that's all you have to figure out. And then you can just implement it. This is for debug, so you can ignore that. But basically, we're going to do some dp, which is exactly the dp I talked about. The code is like, literally this is the entire code. If you have your modulo stuff pre-comped, it's that easy. So this is the number of turns, this is the number of picks, this is k. K doesn't matter, we'll just multiply it in at the end. And then we need to store the answer for this dp. So we'll say the number of turns, the number of picks. And if it's one of our base cases, we just return that. Otherwise, we return the average of the next two things, and that's the answer. And it's that easy. So that's D1. D2 might involve some sort of Pascal's triangle thing. This is very close to like the only difference between average and sum. Like if this were sum rather than average, then you're just evaluating like it's very similar to the Pascal's triangle, right? Pascal's triangle is the sum of like n minus 1 k minus 1 and n minus 1 k with base cases all equal to 1. In this case, the base cases are different. So it's slightly different than Pascal's triangle, but it's still very similar. Because like the transition is all the same, it's just the base cases are different. So it's, well, how do you evaluate it? And I don't know how to do it, but maybe there's an easy way, in which case D2 is very easy. It's something I should learn. It's also possible that you can use the fact that these base cases are special, right? These are very predictable base cases, they're not just random numbers. And, oh, well, I should mention, for D2, you can, like, instead of doing average, you can get rid of this average and make it sum, and then just multiply by 2 to the number of turns at the end. Or I guess divide by 2 to the number of turns at the end. And that will make this the same as sum. So that might make things easier for you. Now you're doing Pascal's triangle, but with different base cases. And also, these base cases have very specific constraints. So you might be able to abuse those constraints. I don't know. Maybe you can just do it in general. I have no idea, because you only have like n different base cases. So maybe there's some clean way of doing it in general. But I don't know. That's above my pay grade. I am, after all, still yellow, about to be orange. Let's take a look at the scoreboard, and then we can move on here. Okay, yeah, looks like I passed. I'm pretty confident in my D1 solution here. Pretty confident that's right. So yeah, looks like about 200th place probably, maybe a little better. Some people are failing B, but yeah. Top 200, not bad for Div1. Awesome. Thank you for watching. I hope you had a good contest. I had a pretty good contest as well. I'm happy with it. And next time, we're going to go for red. Next time, we have another Div1 round. Try and earn the color back. When is that going to happen? January 27th? That's in a couple days. When is that? This Thursday. All right. I will see you guys on Thursday. Good luck, have fun. Make sure to get some practice in. See you in the next one.